Orthogonal trajectories. An orthogonal trajectory of a family of curves is a curve that intersects each curve of the family at right angles or orthogonally. For example, a line that goes through the origin of the circle is orthogonal to the circle. We know that if the two lines are perpendicular, then their slopes are the negative reciprocal of each other, or the product of the slopes is -1. And so if we have two curves, f and g, the two curves are said to be orthogonal if at their intersection x0, y0, any arbitrary intersection that is, the derivative df at x0, y0 is the negative reciprocal of the derivative of g at x0, y0. And so the two curves f and g are orthogonal if at any point of the intersection their slopes of the tangent lines are negative reciprocal of each other. The reason why we don't want to use the term perpendicular because it is not in the sense of a 90 degrees using two straight lines. So for example, given the curve f, any curve that intersect this curve orthogonally or form a 90 degrees angle is called the orthogonal trajectory. For example, find the orthogonal trajectories of the family of curve x times y equals a, where a is not 0 and arbitrary constant. We first start with y equals a over x, so we isolate y. And since we are looking for the orthogonal trajectories, we have to find the derivative, which is the slope of the tangent line. The derivative is -a over x squared, which we can separate these and write it as -a over x times 1 over x, which is -y times 1 over x, or -y over x. We know that this is the differential equation, dy dx equals -y over x. Any orthogonal trajectories to the curve must have a slope of dy over dx equals x over y. And that is, since the original curves have the slope -y over x, the orthogonal trajectory have to have the negative reciprocal, which is x over y. And we see that this is the separable differential equation, y dy equals x dx. We integrate both sides of the equation with the corresponding variable, y on the left and x on the right. We have y squared equals x squared plus 2c. And we recognize that this is a family of hyperbolas. For example, if a equals 1, then we might have y equals 1 over x. And so a family of orthogonal trajectories perhaps would be something that looks like this. Orthogonal at the point of intersection. The trick to find the orthogonal trajectories of the family is that when we differentiate y to obtain dy dx, we want to relate the derivative in terms of the original function y. So for example, when y equals a over x, we have dy dx, which is -a over x squared, but we don't want to take the reciprocal of this. We want to rewrite this -a over x squared in terms of y and x to obtain a differential equation.